Hi, this is Jeff from the Ozark Mountains. That's in Missouri, in the USA. Today, we have a couple TRS-80 Model 100s that a friend of mine sent me to look at for him. There's also some accessories here that we might get into later. This first one was his first recap attempt, and it didn't quite go so well. He put a nice note on here that said, "Botched cap job, please help." So we'll take a look at this, and we'll see if we can figure out what went wrong. Now, all of us, our first time doing something, probably don't do the best job, so that's nothing to worry about. This one he bought more recently and found out that the Option ROM socket had been mangled. So we'll take a look at that to see if we can fix it, or if we'll just swap in a new socket. It originally had this SuperROM in here, and it may be that when somebody tried to pull this out that they really mangled it, and it might be that this guy is kind of in funky shape, so we'll have to see. I said we jump into this one with the recap problem, and we'll have a look at it. I've got out the schematics and everything already, so let's get started. Okay, let's dig right in here. It looks to be in good physical shape. Look inside the battery compartment. There are some batteries in there already. We'll go ahead and pop those guys out. Okay, looking in the battery compartment, that looks nice and clean, so I don't think this thing's had a big problem with corroded batteries left in it. And we'll pop open the Option ROM access, and that too looks good on this one. So we'll go ahead and remove these 4 screws here. There is a spot right there, and right there, and on that side you can kind of feel it when you run the spudger over it, and then you can just rotate him to the side like so. Opens up just like a book. Oh, hey, here's one problem. I'll get you a close-up on that after we disconnect the keyboard. And I found just recently a really nice way of taking these keyboard connectors loose. I use some needle nose pliers, and I stick it down just right there, and I walk them back and forth, and I'm not pushing down into the board. And that gets us off there really slick. Fortunately, they did a good job designing these things. And all the 4 exterior screws are the same. And all of the interior screws are the same. They're different from each other, but the same on the inside and the same on the outside. Okay, that should be all the screws. And we'll take off the barcode reader cover. And we'll take off all these little plastic slidey things on the switches. I like taking those off now so I don't lose them. Power connector. Ground connector, and we'll pull the board out. These have all these little rubber rings here on this RF shield that tend to pop loose. Okay, here's our board. The first thing I noticed was that our memory backup battery is kind of floppy here. Looks like you tried to surface solder it like that by bending the legs out, and that broke loose. Now I understand this because these are a pain to get soldered in there because they're such a huge heat sink. So we'll have to take care of that. And a few of the caps seem to be a little floppy, so we'll have to look at that. One thing he did mention, and I believe it was this transistor here, that got a little smushed looking and then got hot, so we'll have to pull him out of there and test that. 1, 2, 3, 4, all of those look okay. Got our non-polarized ones in here. Okay, so we'll double check the values of all these things. They're easy to get wrong when you're replacing all of them. And we'll take take a look at the back here real fast. Okay, we've got some soldering here that maybe could use some touch-up. Yeah, same thing over here. A little soldering. This is kind of a good example of a cold flow joint. It's on this thick trace here, and it'll take several seconds for that to warm up enough for the solder to reflow. So I think what we'll do is first we will double check that all the right capacitors are in all the right places. We will solder that memory battery back in the right location. Then we'll touch up some of these solder joints and check that transistor, and then we'll give it a try. One issue with these types of circuit boards is that a lot of the holes don't have any thermal relief. They go into a thick trace like over here. There's no thermal break around that, and consequently all the heat is drawn out of the joint, and it's really hard to get things hot enough to reflow properly, especially when you're working from the back side and there's a thick trace on the top side. You can't get enough heat through the through hole to heat up the other side. So you wind up needing to preheat the board. A thermal relief is where a pad is connected to a ground plane or power plane with spokes. The spokes are there to allow a current path, but is sparse enough to not soak all the heat away from the pad. So if you're trying to desolder that, you can get the pad hot enough to desolder without having to heat up the entire ground plane. One thing I like doing on these particular boards is just walking the component out. That's what I'll do with this battery here. I'm just going to heat this joint from the back. I'm going to give that about 5 seconds or so to get hot. And then I'll pull the component out. If it's like the original battery soldered in there with the 2 legs, and then I'll walk each leg out a little at a time. And that's a little easier than trying to heat up the whole board. So we'll get these straightened, get the holes cleaned out here, and pop the battery back in. Find the positive side of the battery. Pop him through the holes. They made the holes for this battery just almost big enough to work. That's always a pain getting the replacement in there. And I like to just tweak the legs over like that. And then when soldering these back in here, you've got to put a lot of heat into it, because there's so much thermal mass on the tab on the battery. So about 5 or 6 seconds on each leg. Some nice new solder. Now we're going to go through and check each capacitor against the capacitor map. I made this up a few years ago when I recapped my first one, and I like doing this for each system I recap. It's a picture of the circuit board with a color-coded map and table of where all the capacitors go. That way it makes them easy to check. So I will check that all of the right capacitors are in all the right spots, and then we'll check the soldering joints on those. Okay, we have all the right capacitors in all the right places, and they are all in the right orientation, the right polarization, that is. We'll fix some of the solder joints on these, like on this big guy up here. And what I like doing, because of the ground plane problem I talked about before, is trying to walk these out. This one I may not be able to do that too. The legs are quite bent over. I suspect that my buddy may have used lead-free solder on here by the way this is acting, and that may have caused him a lot more difficulty. It melts at a higher temperature, and it just doesn't play as nice as good old-fashioned leaded solder. I'm going to clean up the holes here. Yeah, for this vintage gear, I really recommend using good old-fashioned, 6337 leaded solder. I'll clean up our holes now. Now on this, it goes in this orientation with the negative this way, and because I've done lots of these, I know that you can grab it about right like that, bend it over, and it should pop right into the holes. Except we've got a bunch of solder still on the legs. Now we've got him in there, and we've got enough legs sticking through. So I'm holding the cap from the bottom. Again, we've got some big traces on the top there, so we're going to hold the heat on there for several seconds till it flows out nice. And the front side looks okay. Then we'll trim our legs. Okay, I'm going to get around and do this to the rest of the board. If I find anything interesting, I will let you know. Little handheld shaky cam right here. I've been pulling these caps out just to check everything. Whenever you see this sort of discoloration from the cap having been leaking, I like to try to brighten that up with a fiberglass pin or a brass pin like this, just to make sure you're getting all that schmaltz off of there. Clean it with some alcohol, and then solder your new cap in. So I'm going to go ahead and clean this up with this brass pin just by doing this. And I'll probably spend a little more time cleaning it up. You can see that the silk screen was breaking loose from there because of the leaking cap. But I'll do that over the rest of the board. A little more handheld shaky cam. This is where C85 goes. And as you can see, this is pretty chewed up under here. This always seems to be one of the worst areas on these Model 100s. This pad actually runs a signal over to the anode of this diode, and that's completely chewed up right there. And this one goes to a ground plane. So there's probably enough trace left connected there that's fine, but this we're going to have to use a bodge wire on the bottom to fix. A little more handheld shaky cam. You can see I've had to add a few jumper wires on the back to take care of some torn pads and that type of thing. There's some more over here. This is some of the little 10 microfarad capacitors that have a big ground plane on the top side of the board, and they are very difficult to desolder from the back. There's some of the ones I like to walk out, and this kind of glob right here is an indication of that. It's just hard getting the joint warm enough to desolder or solder, and I think this is probably also a lead-free solder. So I think this is the last area I have to touch up. I'll do that, and then we'll see if it works. I pulled the transistor out that the owner of this Model 100 said got hot, and he said it got kind of smashed down. So I'm thinking perhaps some of the leads were just shorted together. We'll test it here on the component tester, and we'll see what it says. Well, it's recognized it as an NPN transistor, and it says it's okay. So we'll go ahead and solder it back in there, and we'll check this board out. I'm sure you can hear the bench power supply in the background. I've got it set to output 6 volts at 100 milliamps. It's a good way to test things with the current limiting on. That way, if something goes wrong, you have less chance of doing damage. And we'll just go ahead and see how this works. Usually when you turn it on, you hear a little pop from the speaker. And we're drawing about 70 milliamps from the power supply, which is about right. And I do see something on the display. And I know you can't see that. Oh, it's got a real funky spot in the adjustment pot here. Okay, here you can see the LCD, and if I... Oh, of course now it's not going to mess up when it's on camera. You can see how the display is garbled. The clock is counting so that it's running, but previously when I was playing with the ribbon cable, it was flipping out. And the contrast adjustment pot has a real flaky spot in it there. I plugged in another LCD and I had the same exact problem, and I noticed that this pot here for the LCD contrast seems awfully loose, or maybe it's just the knob, but that was making the whole display flicker in and out. I don't know, I'll try hooking the display to it without the knob on it. Then we can kind of just poke on the pot itself to see if it's the pot or maybe it's in the board right there. We'll see what happens. The display is coming in and out, so I think we have something up with our contrast pot there. So I'll try reflowing the solder joints and we'll try it again. This one's being kind of a mystery as to what was going on with the graphical corruption on the LCD, so I decided to get out the Auto 100 Model 102 test harness, which a fellow on the M100 mailing list came up with. It consists of this ROM board, which has a flash chip to replace the ROM, and an LCD, so even if the main LCD isn't working, you can get some feedback. There's an interconnection board back here, which all of your I/O hooks to. The serial port, the printer port, the cassette port, and even the barcode reader port. Also run a series of tests, and you can even write your own custom test if you're into that sort of thing. And it's showing a failure in two places. We're going to ignore where it says the LCD initialization test is failing because we don't have the main LCD hooked up. And where it says FH0, this is a memory test. We only have one memory module installed, which is this one, and that's passing. That's the LCD initialization test. It's okay that it's failing. So it's just checking the clock value and waiting a little bit and checking it again, and the clock increases, so the clock is okay. Checking some other signals. Checking some more signals. This is a serial loopback test, and you see that's failing. The system bus is passing, which is the one I was worried about. That's kind of like the main bus on the machine brought out to the outside world. That all seems to be okay. This is the printer port, the parallel port. It passes. That's the barcode port. There's nothing in the Option ROM spot. There's no keyboard connected, so we're not going to check that. Now that right there, that was a cassette test. It clicked the cassette remote relay and then shut off, and it's not supposed to do that. It should turn that relay on, turn the relay off. I think it turns it on a second time, turns it off a second time, then it goes on to other test. And that's shutting off. And there's only one chip that the cassette relay and the serial port have in common, and that is M34 right here. Oops, you can't see that, can you? Right here, Mr. M34. That's the only thing those two things have in common. That doesn't mean that's where the problem is, but it's a good place to start. And we also know that the system bus is passing, so that means that a lot of our signals from the 8155 that are going to the system bus, going to the LCD, those are probably okay. So we'll see what's going to M34 here and see what's happening. See what's shutting the computer off, because it's completely dead. It's not drawing any current at all. It's like the automatic power off circuitry kicked in, which is rather odd. I got started down the wrong path initially when I was looking at this low power shutdown issue, but I wanted to include all the footage to show you my thought process along the way and how sometimes disabling parts of the circuit so you can manually test it is very helpful. So let's jump right back into the testing. I was studying the schematic for this Model 100 and puzzling about what the problem could be. And I decided to start on the issue where the cassette remote relay is triggered and then the thing seems to shut down. And I kind of figured that would have to be something in the low voltage reset circuit. And if we look at the schematic here, we've got this gate which triggers this transistor that runs up here to the power supply section. And the input to this whole mess is the reset line and this PCS, which is the low voltage reset. So what I did is I pulled up this resistor right here, which is R125, which drives the base of the transistor, so this can't be triggered now. And I'm also monitoring the 5 volts. I've got these hooked up to the oscilloscope. The fuzzy blue trace in the middle is the 5 volts. That's AC coupled and it's set to 50 millivolts per division so we can see any noise. And the bottom trace is the reset signal, which should be low. It goes high when you have that low voltage shutdown or the reset signal. So I'm going to go ahead and turn this on. And when it gets to the part where it clicks in the relay, we will see that the low voltage reset signal does indeed go high. I'm going to turn this on single shot so it'll capture it for us. And right there, that is when the cassette remote is turned off. So the relay's closing. And you see the low voltage reset signal go high, but we don't really see any sort of big blip on the 5 volts. There might be a little negative spike here. Yeah, that's about, oh, I don't know, 40 millivolts low. I don't think that's that significant. And the test actually locks up at this point. So I pulled up R50, which goes over to drive the base of T6, which triggers the relay. So now we're not actually going to pull this relay in. We'll turn on our test again. So this time it's going to do the same thing, except it can't actually energize the relay coil because it's not triggering the transistor to energize the relay coil. Now we're past the point of the test where it says cassette remote fail, and it looks like it's continuing to run for test. Yes, and now it's saying waiting for power off, but we've disabled the auto power off the low voltage reset circuit, so it will try to reset it and it won't be able to, but we'll see the spike going to that transistor, and the 5 volt line is climbing right there a little bit, which is kind of odd. So we've got some sort of glitch that when the cassette remote relay is actually energized and then released, that it causes a glitch which stops the machine from running. And when we can't energize the coil because we're not energizing the transistor for that coil, it continues to run. So I don't know if that means it is in the power supply section, which is a possibility, or if there is a fault with the relay. But why is it when the relay is released? When the relay is released, will cause a bit of a spike. There's a diode snubber across it though, which should help with that problem. I'm not sure yet. It's quite curious. I temporarily connected the resistors we just had disconnected. The resistor that feeds the base of the transistor that triggers the cassette remote relay, and also the resistor that feeds the transistor that does the auto power off. And I set up this scope probe here to measure the low power shutdown signal that goes into this NAND gate here. So we are measuring right at this point right here, right out of the NAND gate. And I let it run through its cycle, and as soon as the relay clicked off, we did get the low power shutdown signal. But what is generating that? The not low power shutdown is coming directly off these transistors. It's kind of a little comparator. And that's being fed down to this NAND gate, which sends the positive acting low power shutdown actually to the trap input on the 8085 microprocessor. So there's something about that relay triggering and then releasing that is causing that analog signal to be generated, I'm assuming at the input of the invert or input of the NAND gate. Either that or it's something in the NAND gate itself that's triggering the output. So what I did is I lifted this resistor again, which goes to the transistor that triggers the relay. And it is connected to this lead now, and I will touch it over here to the 5 volts, which should trigger this relay. And if it's just the relay being triggered that is causing a low power shutdown signal, then we should see that on the scope. Okay, I've got it on single shot. I'm going to run our clip lead over here and touch the 5 volts. That should be here. Relay's triggered, released. There's nothing about me triggering and releasing the relay. So it doesn't seem like it's the relay itself or the transistor driving the relay. So maybe it's something generating the control signal to drive the relay. When we are manually triggering our cassette remote relay by lifting this resistor on this end and applying 5 volts there, we could trigger and release the relay to our heart's content, and the computer ran along merrily. But you see that transistor is driven by this inverter gate on M34, which gets its signal here from not remote. Not remote comes from M14. So what happens if we apply ground directly to the input? That's pin 3 of M34. Note this pull-up resistor here. So we have to pull this line low, that is to ground, to trigger it. That would be simulating exactly what the computer is doing. So let's see if that causes a problem. I'm going to start up the test here, and it doesn't matter what this is doing. It's going along its merry way. Make sure we've got our resistor connection here. We'll get M34 pin 3. Trigger the relay a few times. And look at this. Our LCD stuck. The computer's actually stopped. So there's something with using M34 that's causing a problem. Interestingly, M34 is also used here on the RS-232 circuit, as well as in part of the LCD circuit. So maybe all 3 of these strange failures have to do with that one chip. Right now I have no better idea, so I will grab a chip out of the parts donor board and we'll try it out. We pulled M34 from this board and swapped in the M34 from the other board, and since it was a pulled chip, I just soldered directly into the board. That way we don't have any problems with the pulled chip not wanting to plug into a socket nicely. And lo and behold, it ran all the way through the test just fine before it tried to power the system off at this point. Now it still didn't power off because I have this resistor here pulled. I'm going to solder this resistor back in and we'll hook up the rest of the test harness. And we'll see if that took care of our other problems too. Silly me. When I pulled M34 from the donor board, I also pulled this transistor. If you remember, the transistor originally in this place, the owner said had gotten really hot at one point. And although it tested good on the component tester, I still wasn't quite sure about it. So I changed out both at the same time. And then we tested it and everything seemed fine. I hooked up the rest of the test harness. And as soon as it triggered our cassette remote relay, it died again. I was very, very confused. And then I noticed that with the rest of this test harness hooked up, you know, this additional board with the LEDs and chips and all this type of stuff, that it was showing it was drawing about 20 milliamps more on the bench power supply. So what was happening is that it was already about 82 milliamps in this configuration, and as soon as that relay clicked in, that was over 100 milliamps. The power supply went into constant current mode, the voltage dropped, this went into under voltage, and it quit. So the original problem when we were testing without the additional test harness hooked up with just the ROM board was that this switching transistor was not up to the task. So changing that fixed the original problem. I bumped up the current limit on the power supply, and it will now run through the relay test just fine. We still have a problem with the serial loopback test. It's not receiving the correct data, and we still have the graphical corruption issue on the LCD. And I'm going to start looking on the LCD with all the chip select lines to make sure they're all getting from the 8155 up to the LCD connectors. That's what we'll do next. A little handheld shaky cam here. This is the unit we're working on, and this is a known good unit. What was happening with the unit we're working on here wasn't making sense, so I started measuring the various bus signals with the oscilloscope. I saw a few signals which didn't look right, so I got out a known working unit as a basis for comparison. And I'm using a little jumper lead here to go from AD2, address and data line 2, doing the same on both. The yellow trace is this working board, the blue trace is this non-working board. And looky what we have here. The little spike here is nothing to worry about. The address bus on the 8085 microprocessor is multiplexed. So as it's kind of changing states, latching the address out, you'll get little spikes like this. It's nothing to worry about. However, this little stair-step type of thing is not normal. That is a good sign of bus contention, and I found that on 82, 85, and 87. And then I got to wondering, I was like, well, hey, if there's bus contention, I'm probably drawing some more current. So I looked at the amount of current. When you start it up, it'll draw about 62 milliamps, and then it'll drop down after a little while, whereas the working unit will draw about 46 milliamps. So there's definitely something happening on this unit that's drawing about a third more current than it should, and it's causing some bus contention. But there is a lot of things on that address and data bus. And the interesting thing is, if I can show you here on the schematic, address lines 0 through 7, this is address and data, come out to M2 here where they're latched out, and this goes to most things, but they also go to M1 where they're latched out as the address lines. So you have M21, M1, latch out and buffer the address lines, and M2 is our data lines. And if we measure address and data here, it's not messed up. It looks the same on both boards. On this side, it is messed up, so it's something on the data bus, but there's a lot of things on the data bus. So, yeah, there's ROM and RAM, all sorts of blue logic ICs. We've got the LCD disconnected, so we know it's not that, but we know the LCD is good. We have to figure out maybe what's unique to the 3 lines in question, AD2, 5, and 7, which is probably everything. And then try to make an educated guess as to what chip might be hanging it up. None of them are getting particularly warm. And it's kind of amazing the computer's actually working as good as it can. Or It's actually amazing. It's really early. I woke up about 2 o'clock this morning. It's amazing the computer's working as good as it is with this sort of problem. So the big problem we have here with the data lines having the signal coupling is what it looks like, or two things are trying to drive the bus at the same time. There's some form of contention, is that there's so many things on the data bus. And there's only a few things that we can pull and still get it to run. One is M15 here, which is the latch for the keyboard. We can pull that and it'll run without it. And we can pull M23, which is a similar latch for the RS-232 stuff, it looks like. So it may still run without that. Other than that, the RAM chips themselves tend to fail quite a bit. So we could pull that, put in some socket strips, and I've got some known good RAM modules we could pop in there. So it's kind of a conundrum. It could be contamination on the board somewhere. Trying to measure, the resistance between the traces and ground, traces and VCC don't reveal anything. So it's kind of a conundrum. I changed my mind in the order I was going to do things, and I gave the board a good wash first to get rid of all that nasty flux. I had that cause me a big problem in the last few days on another machine. So I got rid of that first, and of course it didn't solve this problem. So the first chip on the data bus I pulled was M15, which is the keyboard buffer, and that didn't do anything, but the computer will run without it. The other thing on the data bus the computer will run without is M23, which is also on the data bus. It's another latch. So when I pulled M23, I saw this. You see, we still have this little spiky bit here, which is fine. That's just when the address/data bus is latching because it's multiplexed. But we don't have the bus contention anymore. So something with M23 was causing that, or something triggering M23 is causing that. So at least we're on the right track now. M24 pin 7 is what enables M23. See, I've stuck this back in there loosely. And with M23 in place, we see a lot of noise, a lot of craziness on pin 7. With M23 out, we don't. Which does not make a whole lot of sense, because the signals feeding into here should have nothing to do other than enabling this. Let's just read in Y5. So let me see if I can show you that on the scope. Here is the noise that's on the enable pins of M23. This is actually not coming from M24, it's just being fed back into M24 from M23. As a bit of a secondary test, I took M15, which is a 40H244, same thing as a 74HC244, from M15, and I moved it to M23, which is the same chip, and I held it in place, powered it up, checked pin 7 of M24, and lo and behold, there was no crazy noise. So the problem indeed was M23. So I will go see if I have one of those, or I will pull one from the parts machine, and we'll solder these in and see if that takes care of our bus contention issue. Okay, the original M15 was soldered back in, and I borrowed a chip from the donor board and I soldered in here in place of M23. And I've got all this hooked back up, and as well as the full test harness. And one thing I will say is that with the bad chip replaced, it draws 20 milliamps less, just like our other good board that we were testing with. Now I'm going to turn this on, or back on actually, and let it run through the test procedure one more time. And then we'll put it back in the case and test it again before calling it good. It starts out with a RAM test, and it'll test all the ports and do things like that. Oh, one other thing I did was I replaced this header strip right here. The one that was in here had a couple spots messed up with solder, so I pulled one out of the donor board. And I still need to double check that this pot is going to work okay. If not, I will swap in that from the donor board as well. Now you might be asking yourself, how did this computer work at all when 3 of the data lines were so messed up? And that's a darn good question. It all comes back to the old quip about if a tree falls in the forest, does it make a sound? Well, of course we know it makes a sound, it's just that nobody's there to hear it. And it's the same way for these data lines. While the signal may have been messed up, if there was no other chip listening to the signal at that time, it really didn't matter. But when there was a chip listening to that signal, it did matter. What you're seeing here is a slow motion of the test screen that the test harness puts out to the main LCD. The first 30 seconds shows the problem as a result of the bad M24 chip, and the second 30 seconds is after it was fixed. And you can see that just depending on the state that those data lines were in at a particular time gave us a really random and strange looking screen that was really difficult to figure out. This type of problem can really throw you for a loop because you can have some very strange effects from it. Well, we got one computer fixed, so it seems like a good time to take a break, and we'll come back and do the second computer and the accessories in the next episode. This one sure threw us for a loop with that bus contention problem, and I got led astray a little bit at first with the low power shutdown issue. Now the thing was, I just worked on 4 other Model 100s with the same basic test setup, and it worked fine. So the fact that I had the power supply set to only 100 milliamps really didn't register with me. And it just so happens that this bus contention problem was drawing enough extra power to allow it to go into a low power shutdown mode. Who knew? Luckily, I had a parts board to pull the needed chips and pin headers off, which coincidentally was thanks to the same friend. He had this laying around and he gave it to me last year, and it really came in handy. Next time, we'll take a look at this Model 100, which has the mangled Option ROM socket, which we'll try to fix, or we might just pull the one out of our parts board here. Now, sometimes it happens if you have an aftermarket Option ROM that doesn't quite fit in the socket and it goes in there too far, and then it's really, really difficult to get out without mangling something. And that may have been what happened, but we'll have a look. And then we'll take a look at what the SuperROM does, and we'll also look at the REX CPM that my buddy sent along to test these with. I'd like to take a moment and say thanks to folks who help support the channel through Patreon and other means. It's greatly appreciated, and it's because of you that I can keep this channel going. If you'd like to find out some information about becoming a supporter, well, if you look down below in the description, you'll see some links there. If you're a subscriber, thanks. I really appreciate it. That helps other people find the channel too. If you're not, well, what the heck are you waiting on? If you look down below, you'll see a rectangular box that says subscribe in it. Well, click on that dude and you'll be subscribed to the channel. Then you'll see a bell-shaped icon. Well, click on him and YouTube will be nice enough to let you know just as soon as I post a new video. If you have any questions or comments, well, you know what to do. Leave them in that comment section down below. I would love to hear from you. While you're down there, go ahead and give the video a thumbs up if you like it. If not, well, give it a thumbs down, but just let me know why. Well, until next time, bye.